Hello everyone. I wanted to work a problem from section 9.5 and I'm going to get to that in a bit. I'm taking a bit of a circuitous path here. You know my nature is to sort of do a review if I can and touch back on some important ideas. So I'm actually going to start this with what seems like a absurd question for where we find ourselves right now in the textbook. Namely, I'm asking you, how many lines are there with a slope of 1? Now I popped that question to you back in chapter 7, or excuse me, chapter 8, and the answer was that there are an infinite number of lines with a slope of 1. And I had this particular image here to justify my reasoning on this. Here you see 5 lines that all have the slope of 1. Now let me magnify this because we need to look at this with a little more detail. Okay, now what I'm suggesting here is that you think of this line, which I have said is probably the most important line in Math 122, the line y is equal to x, as a cognate, so to speak. You know, a root word that other words are built from. Like many of our English words come from Latin cognates. In other words, really what we have here is a family of lines. This line right here has the same cognate as does this line, as do the ones marching off in the negative direction. And the idea here is that these two are essentially the same, except all the y's are going to be increased by 1. They're all going to get bumped up by 1. The input is going to stay the same, but the output will be increased by 1. Here the input will stay the same, but the output will be increased by 2. And of course you can continue on doing this with fractions and with other whole numbers as often as you want. So there's an infinite number of lines marching this way and marching this way. This idea is called a translation, and you will see it in college algebra, where you shift the location of a graph. You don't change its shape, you simply shift it in the xy axis by altering, adding and subtracting to your x's and your y's. In this case we're altering our y plus 1, plus 2, plus 3, etc. Now how does this play in our problem at hand? Well, before I march there, I wanted to take one more look. We've looked at lines. I want to look at quadratics. And here are 3 quadratics. And if we were to use a grapher and graph these are all going to graph with the same shape. These are all from the same family of curves. And that's because the coefficient in front of the x is the same in each case. Now, in particular, what I want to look at are these two right here, because the cognate here is identical in each case. The x's are going to be treated the same, but what's going to happen is this one is going to be shifted down. Every y value is going to have 1 subtracted from it. So all 3 of these are going to graph the same, but in particular these two are going to be almost identical, except this one graph is going to be shifted down by 1, translated by 1. So what I thought we'd do is bring in a grapher that I like, and as you can see, I've graphed these two. The red one is the cognate, if you will, and the blue one is the translation 1 downward. And so you can see the blue one sits below the red one, and you can see the vertex is about 1 down from the other vertex. And the same is true here. I mean, these look like they're running together, and that there isn't a space of 1 in between here. But if you track this over, y is equal to 8 right here. This is so steep at this point, and by the time you get down to the blue, you've actually gone down, step down 1 to 7. So that's the idea of translations, and that's going to play large in my discussion of this particular problem from the 9.5 section on logarithms, which is right here. They ask us to graph, this is problem 66, they ask us to graph and state the domain and range of this function right here. And it is natural logarithm minus 1. Okay, so I think we can do that, and I'm going to show you my first move is to rewrite this as a equation in x and y. So I replaced g of x with y, and now I'm ready to set up a table to graph this. Now, of course, no one really graphs these things by hands anymore, but we ask you to do it 1 or 2 times, and then from then on, use your graphing calculator or Wolfram Alpha or a graphing website. So if I was going to set this up to graph it by hand, I'd probably create a table that looks like this. It's a little more involved. In other words, what I've done is I've sort of pieced this thing apart. First our input, and then our input goes into the natural logarithm function, and then I take that and I subtract it by 1, and of course this is the same as y, that's our output. And you'd run some numbers, and I did that. I've got some that I'd like to show you. Here are 2, where I let x equal 1 and 2, and these are the values that came out. And it's nothing more than punching buttons on a calculator. And I thought I'd show you that too, because a lot of this section deals with calculator work. So I'm going to run a line here of data where I'm going to let x equal 10. And so here's my computer calculator, and I input 10, and here's the key for finding out the natural logarithm of 10. And I would get a number that never ends and never repeats, so I'm going to have to truncate it. I believe I rounded this to the thousands, so I'm going to have in the ln x column here 2.303. And then I would subtract 1 from that, and I would have 1.303, and that of course is my y. So let me drag that line of code in right here. This was for x is equal to 10. Now, I only have 3 points, and it would behoove me to do a few more because this isn't a straight line, it's a curve. And one number that is missing that's glaringly obvious is x is equal to 0. That's a number that you'd naturally run. And I wanted to show you what happens when you let x equal 0. Let's clear this, input 0, and hit our natural logarithm function, and it says no number. It says negative infinity. In other words, this is undefined for x is equal to 0. And so what the calculator is telling me here is that basically this, as x gets closer and closer to 0, the natural logarithm function approaches negative infinity. It's not a number, it's a direction, it's an idea. And so the negative is going to increase dramatically as we get closer and closer to 0. But it's undefined, it's not a number. And so that is what our line in the table has to reflect. And so here it is right here. When I let x equal to 0, I get NaN, not a number. Now you can graph more points, and I certainly think it would be important to graph something between 0 and 1, since we know as we get closer and closer to 0, this thing is going to get enormously negative. And you'd probably want to graph a few other points farther to the right, like perhaps x is equal to 20. I am going to stop here in terms of generating points. And I'm going to drag in my graphing calculator again and show you another page here. Here we have the two functions. Here we have the cognate, ln a graph of y is equal to the natural logarithm of x. And here is the same equation with 1 subtracted from it. The red one is going to graph above the blue one because the blue one is a translation down by 1. And so you could see that this distance right here appears to be 1, and it is. And from this graph, once you've done this, you can read off the domain and range, which they asked. Notice that there aren't any negative input values allowed. It's undefined into the natural logarithm function. And we did 0, and we saw that it was going and trending towards negative infinity. So 0 is not allowed either. It was not a number. So the domain is going to be all x greater than 0. Now what about the range? Those are the y values that are generated for all our input values. And as you can see, it's going to, in the negative direction, we're simply going to get larger and larger, negative. And so this one part of the range is going to be towards negative infinity. What about in the positive direction here? This thing seems to be sort of like getting shallower and shallower slope, and is it ever going to reach up to 10 or 100 or 1,000? And the answer is it does. It just does so at an exceedingly slow rate. So the range here is negative infinity to positive infinity. So that's the reading of the graphs and the domain and range. I hope this helps. It's a bit tedious. We don't graph these by hand. Just do one or two and then use this tool and the link I've given to you on the website. Okay, I'll be talking to you soon.